I feel like every year when I'm doing the PLS lecture, my eyes are itchy.
Oh, yeah.
Every single year. This
Yeah, because I don't want to risk putting the contacts on again. Monthly.
Yeah.
Oh, it just keeps going. Blah.
Did not know that. Um, Let me get the chat up for Zoom as well. Okay. Everyone, we're doing the PLS tutorial, and so I hope people could hear me online too. But just heads up, we're going to go through an easier part, but then the math part. And so if you're confused at any point, just stop me and then we can discuss. And hopefully we could get to the part when I show the code. But if not, I have shared it on our the Discord channel, so you could also just follow through that to have an example of how to run it. Um, Also to define what I mean by you're lost, like if any point in your head you're like, wait, that's when you have to raise your hand. Okay, just stop me right there and then. Okay, so so today I'm going to talk about partial least square correlation, and some other multivariate methods for imaging, neuroimaging data, but I'll focus on PLS too. Is this? Oh, I need to click on. Okay. So I'll talk about what it does in general first, and then I'll start with the classic PCA because PLS is looking at the relationship between two sets of things. So imagine it's like a multivariate correlation. But it all stems from PCA, which works on a single data set. So I'll start with that and give you an example of how something similar to PCA could be applied to look at functional connectivity and how that would help us understand functional connectivity data. And then I'll go into PLS with an example of the brain behavior correlation between cognition and functional connectivity. And then this will be the parts that are probably more heavy in statistics, where we talk about bootstrap permutation, the reliability of the outcomes, and then hopefully we'll get to the example. Okay, so let's start with what is multivariate analysis. So multivariate data are a lot of data that we see nowadays. For example, you might have questionnaires, you might have images, and in our case, we have like voxels or parcels in the brain, and they all have the same feature that it's very complex. There's just a lot of them that it's very hard to just eyeball it and see anything, right? So that's why we need multivariate statistics to help us extract the needle from the haystack because this is a mess, right? So that's why we're going through like all the pre-processing steps but what multivariate methods does is that instead of treating each individual value as an independent measure, it takes into account how they related to one another and extract the most prominent pattern from complex data. And actually, you have already used it today when you use these apps, because that's like the basic things behind all of these algorithms, and even I don't know if AI probably has it, but machine learning as well. It's what helps us extract like features or the most important information, in other words. So To work with multivariate data, we use the methods that could extract common characteristics. Oh, sorry. This is just the common characteristics of the data that you often have more variables and observations, right? So, for example, in your brain, you have, I don't know what is the usual number. Like for functional connectivity, we have like up to 76,000 variables at the minimum. And but we cannot collect 76,000 participants. We at most like okay, 1,000 is already a big sample size. So you have the issue of you have way more variables than your observations. That means you're describing something like a lot of them with a small number of it, and that will lead to overfitting, which the traditional analysis cannot handle. So that means when you are looking for signal, you might be finding the noise instead because there are just too many observations of them and you're overfitting it. And that means it will be very hard to generalize it to other data sets. And also because of this feature, some usual assumptions of traditional statistics might not hold anymore, especially in the univariate, because when univariate statistics are developed, they're developed when computer doesn't exist. So you're basically hand computing your T statistics, your Z statistics. But nowadays, with the format of the big data set, they might no longer hold. And so that's why we turn to multivariate statistics, and the goal of it is to extract the most important information. That's the main thing. Okay, everyone with me? I think this should be okay so far. So let's start with the classic, so the PCA. Um, So PCA, you start with your data set. So imagine this is like just an Excel sheet or a RADCAP file if you have participants or observations on the rows, and then on the columns you have the variables. What PCA does is that it describes the same set of observations, but now with a set of factors. And these factors are a linear combination of your original variables. And in PCA, the first component will always have the maximum variance in the data. The second component will have the second most, and so on. The factors are in different names, and that's when you will see these in the literature. They could be called component, principal components, dimension, latent variables, but be careful when you see these. Sometimes they mean different things. Sometimes they mean these values. Sometimes they mean the scores. Sometimes they mean the two and like combined. So just be careful about that. And these factors or components in PCA are what we call orthogonal. And that means statistically they're uncorrelated. So when you take a Pearson's correlation, you'll have a correlation of 0. And that means statistically they are independent from each other. And what that implies is that you can interpret them on their own. So changing the scores of on one factor will not affect the scores on the other factor. And so you see that PCA goes from a set of variables that might have shared information down to a smaller set of independent information. That's so you often hear people say that PCA does dimension reduction. So it's also known as a dimension reduction method. So what it's actually doing behind all that math, let's call it math, is this. So we're trying to extract the most information. And there's a really nice analogy by Dr. Alison Horst that creates this figure. So you're in the ocean and imagine you're a hungry whale shark. You're trying to like swim through this crowd of shrimps and trying to get as much as possible in like one go, right? So you're a whale shark. And so you're trying to align your mouth to capture as much as possible in one go. That's what we're doing for PCA, right? Imagine. So assume we have two variables. You could always represent them with a scatter plot. So I have A on the x-axis, B on the y-axis. I have all my observations shown by the dots. Now I'm a whale shark. I want to find the line that captures the most variance in the data set. Basically, it goes through the cloud of the dots. And so you could see that it's capturing most of the variance in the data set. So PCA find this line and then use this as the new variable. And we just call it component. This is called principal components. Now we can quantify these dots with these new axes now. Right, so now you have a new scores. And this rotation is what that linear combination that I showed earlier representing. It's basically a rotation of your axes. So in short, PCA use these components as new variables. And the first component best explain the variance in the variables, and the second component explain the second most, and so on. And here you see that they're orthogonal, like literally orthogonal, and they're also independent from each other. So how do we interpret the components? In PCA, usually we do that post hoc. So you will need to look at the other information you collected on these observations. And to understand what the components are, we look at what's driving this progression from one end to the other end. So for example, if you have younger people on this side, older people on that side, then this first dimension is basically capturing the progression of age, right? So I would define my component one as the age component. And another example, if I have all the males on top, females below, then my second component is capturing the sex factor, right? So basically, when we're interpreting components, we're looking at what's basically on the two opposite end. Okay, so to sum up, multivariate method extracts these components, dimensions, or factors, and it performs the dimension reduction, and it helps us visualize and quantify the most prominent pattern in the data. Is everyone good so far? Everyone with me? Yes.
Go back to determine what components capture one again. Like how did you know that component one is actually
Like this?
Yeah.
So yeah, so it's not from these dots. So I have this data from whatever, maybe their social Cox scores, and I extract this pattern, right? I need to have like the demographics data I collected from them. So it's external information that I got on these observations. And then I looked at how they are related to this map. And then I can define it this way. So that means if I did not collect age, I wouldn't know it. So it depends on what you have in your data. But the nice thing is you don't have to include this in when you do PCA, which means age is an independent variable from building the components. Yeah, no.
Oh.
So age is not my variable A or variable B. Age is just something that describe these participants on the side. Often you will have this issue when you're analyzing data, like, oh, should I include age? Should I include education in the analysis? What I would always suggest for when you're running PCA is to leave them out and to extract the component only based on the most important variables that you're interested in, and then try to map these back onto the space, which will help you define the component. But if you include these things in the components, then it's very likely that this will drive your components. Usually when you include age as like one of the variables, you will find the first component is just age. And sometimes it wouldn't be very helpful, right? Yeah.
And question helps it.
Yeah.
So then you would basically you're saying you don't generally put demographic in the analysis,
I usually don't.
and so you just like if you were using social cog, all right, for example, just put the social cog.
I'll just put social cog
and then yeah,
and the fMRI, and then I will use age or demographics as extra information to help me interpret the components.
How about visualizing age from?
How about residualizing age? So that's a great question. So what I would do is, remember when I showed the data set, I will regress it there. So you use a regression model, you take the residuals, and then you do the PCA.
Okay,
That makes sense?
yeah, because that's how I usually do it, but I would.
Yeah, that's fine too, if you want to remove the effect of age.
Because I was wondering if there's like cases where it would be preferential not to, but and then as you said, use it as context.
Mm-hmm. Yeah, so for example, this is a very common case for like aging data set. Like I don't want to remove age. I want to see where age is in my variables. So yeah, if you want to remove age, that's what you could do. But I would still suggest like you remove age and extract the components, but still try to map the age, and you will be able to see if the age effect is already removed. Because sometimes you might removed it, but you still see something here. Right. And if you have removed it completely, then you should see like a scattered pattern when you map age onto your components. And that would just verify what you've done. Makes sense. Yeah, that's fine.
Sounds so stupid. Very sorry.
No worries, we're all stupid.
Components, you said they're orthogonal, right?
Yeah.
So how are you gonna map it onto it? Is it because of the spread? It looks like it could be age effects, or because if you, my thinking is if age and principal component one are orthogonal.
Yeah.
How could you correlate to figure out the spread? Like how did you determine who's age? Just because you can see there's a spread across time?
Yes.
Okay.
So when you interpret the components, so for example, when I'm interpreting component one, I kind of ignore my component two. I only look at their projection onto my x-axis. It's just that I don't visualize it that way. Like, but I would also just look at the progression like
I see.
along like the horizontal axis. I got a question from online. So does that mean we can only include independent variables in PCA? No. So that's the great thing about PCA. It will not be affected by multicollinearity. And in fact, if it's multicollinear, you would be able to see it from PCA. It will tells you how similar these variables are on these components. Yeah.
let's say you're working with cognitive scores
Uh-huh.
and you want to use PCA to kind of extract cognitive contours,
Mm-hmm.
not regarding demographics,
Mm-hmm.
age or sex.
Mm-hmm.
How can you do that? I'm just confused of how you interpret your results. If you put cognitive scores,
Yeah.
see how
Yeah.
do you interpret on a cognitive?
So for example, here, if I have my cognitive scores. Oh, so that would can I leave that for later? You will be able to answer that question by the end of this presentation, I swear. But let's leave that for later. So no, we're not having spoiler alert. Okay. I'm happy we have so many questions just for PCA. So, okay, so let me show you a quick application to brain connectivity. Is everyone familiar with brain connectivity? I assume everyone has done the module, kind of. Okay, so just a quick recap. We looked at the bull signal, we look at how synchronized they are, and then we end up with this functional connectivity matrix. And by looking at the clusters in the connectivity pattern, we could get these different networks, right? And the the ball signal from the same network should be more synchronized, and from different networks should be less synchronized. So these are the networks we have. Default mode. Okay, so the main thing I wanted to mention is connectivity data is high dimensional. So here I have 392 brain regions using the Glasser cortical parcels with 10 subcortical parcels. And just by looking at this one person's connectivity matrix, I have like 150,000 values. And even if I take away the lower diagonal, the lower triangle and the diagonal that is probably not informative, I still have like 76,000. That is enough, right? The other question we have is, what is the real variable in functional connectivity? Is it the regions that we care about, or is it the connectivity per se? But also, if you think about it, can we really think about how two regions are connected without thinking about how they connected to the rest of the brain? Can we just look at the connection one at a time without looking at them all together? My short answer to that, or my personal opinion to that, is I think brain is a system, so we should consider everything all together instead of just looking them one at a time. Yes. 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 So the question is, does each parcel only belongs to one network? The answer is yes. Usually yes. But it depends. So sometimes this is the canonical network. So we tend to cluster these brain regions into like different groups, but there are also different ways of grouping them. So for example, in my own research, we also categorize them into like social processing networks. And that means the same region could be categorized into, for example, default mode, but also maybe a mentalizing social networks. And I think this all comes down to this,
It all
de-
depends.
yeah,
So
how it's
in this
defined.
case, this particular picture is of networks that were defined based on RY, whatever RY got a cluster assignment.
Mhm.
So therefore, there's each time you run connectivity pieces and you treat parts of all belong to one, but you can do like different types of like. So it depends how you define network. In this case, network is predefined inside the atlas as a label because somebody did a clustering algorithm and assigned it to a network.
Mhm.
I see this.
That makes sense so far?
Yeah.
Okay. So when we analyze brain as a system, if you've gone through the metrics, the modules, you will know that there are some metrics that describe the system. So we call them the graph theory metrics. I see Hassan is excited about it. So for example, you might have heard like segregation, modularity, like these terms, those are all from the graph theory metric. So it's looking at the brain connectivity as a graph, and these metrics are kind of describing what this system looks like. But alternatively, we want a more comprehensive view, and that's why we use the multivariate analysis. So an extension of PCA, it will help decompose this brain correlation matrix into a map, like the components, and they could be in different names depend on the analysis that we use. And it gives you a map to visualize the brain as a system. So here, the closer the two networks are, that means the more similar they are. They will have higher functional connectivity. They're more synchronized in the pattern captured by the components. So just to Okay, I'm trying to think about how to say it. So this method is called cuff status. It's an extension of PCA. It's not the main point of our presentation today. I'm just showing it because I'm going to use it as my example for later PLS. but we can read this map like a PCA map. So I call them dimensions in this study, but you just understand them as principal components. So in this method, what I did was I have everyone that has this connectivity matrix. I first take a linear combination of them to create the pattern that best represents everyone together, right? And then I do a non-centered PCA and I get this map. So in this map, I have the dots representing a region in the brain and colored according to the networks. I can compute like the mean scores of each network, so the triangles on the map. And so this is looking at everyone from the group level, but I could also project the individual connectivity pattern onto the space to look at what these regions are when I looked at it from the individual perspective. And then I could see how wide is spanning to quantify the heterogeneity of this region or of the network. So if that part is like too fast for you and you don't understand, but you also don't need this analysis, then feel free to just forget it. But if you're interested, feel free to come talk to me afterwards, and then we could go more details into it. So I first get this map, and then my next question is, how is this related to my behavior? And I'm already doing multivariate. I don't want to go back to correlations on all like 392 regions, right? So we need a multivariate way to do association, and that's where we bring partial least square methods. Okay, so finally, we're going into the topic today. So partial least squares methods describes a family of methods, and the most famous ones are partial least square regression that you can think about as a multivariate regression, and the partial least square correlation that extracts the commonality. There's also another one called partial least square SEM or partial least square path modeling. It's more like a path model in the multivariate framework. But I'm not going to cover those. And so just quickly, PLS regression comes from econometrics and chemometrics field. Partial least square correlation comes from psychometrics, ecology, epidemiology, and then was proposed for neuroimaging by Randy McIntosh from the Baycrest in 1996. And there's a very nice summary by Krishnan et al. In 2011 that I highly recommend. I'm showing this just to let you know that these methods are from different fields. And that means sometimes you will see different terminology when you look at papers from different fields, but they might have mean the same thing. So just to be aware of that, you might have different names that means the same thing, and sometimes it's just because they came from different field. Okay, so partial least square correlation is the main thing that we're going to talk about today. It could be under different names. So sometimes you will see people just shorten it as PLS, but be careful because sometimes people means PLS regression. They will also just shorten as PLS, which is very helpful. And so just maybe take an extra look at the method section or, the description to make sure that it's a PLS correlation or it's a PLS regression, because you would kind of understand them differently. It's also I think its original name is interbattery analysis or like co-inertia analysis. They mean exactly the same thing. The goal of PLS is to relate two sets of variables and looked at their multivariate associations. And it's an extension of PCA. Okay, so visually. So now we have two sets of data. So I have the original variable A and B, and now I have another set, X and Y, and I want to look at how correlated they are, right? So for PLSC, we're still finding the line, but now I'm getting the lines from the two sets simultaneously so that when I use this as my new variables, in PLS we call them latent variables, they have maximum covariance. Make sense so far? this visualization? Yes. Okay, so let's go back again. So remember that we're finding the line in PCA. Now we're doing it in two sets together. And in PCA, we're finding the line that captured the maximum variance. But in PLS, we have a different purpose for this line. In PLS, this line should have the maximum covariance. Does that make sense? Which part is confusing for you?
So it's on like stupid, but almost like
No worries.
the figure, how like they're both running off the direction and it's like cool.
Oh, you mean like this?
That might be, it's just like kind of weird. Right.
Oh, I see. So this is completely arbitrary.
Right.
First of all, the data is fake.
Yeah.
And it's the same data if you can see, just with the rotation. So I'm just showing you that this line could be capturing different parts of the data in the two sets.
And then we just like map them and see how those two lines.
Yeah, but so instead of just finding the line that goes through the dots that capture the most variance, in PLS, we're actually finding the line where when we put them together, they will look like as similar as possible to each other. So have maximum covariance, yeah.
So where do you get when you just
Yeah, there may be like.
What?
like you have the
Mm-hmm.
where do you get your X and Y?
Oh, I see. So there were here. So I could also like rotate the space to look at the new axes. But we are visualizing it in a different way in PLS. That instead of looking at how component one related to component two, or how we show them in the same space, usually in PLS, we're showing one dimension at a time. Because of this, because we're describing two sets of variables and their associations. So we still have the idea of the new axes in the original data. Like I could still just rotate these two figures and then treat this as my component one, as my like new variable one, and this as my new variable two. I can do that, but it's just not how we usually visualize it in PLS. Does that make
I'm not sure.
sense? Like, are you trying to ask where are the new axes?
Just having your hard time how to go from this to the next.
Oh, I see. So go from this, I project my scores onto this because this is my new axis now, right? And then I can now quantify them. I get new scores on these axes. And then I just have a simple scatter plot with those scores. So this is the same as this. And that is the same as this. And then I'm just plotting a scatter plot with this x-axis and that x-axis. And I got this new plot here. And you should see this trend because this is what PLS is maximizing, is the covariance between these two axes. Make sense? Hassan, do you still have a question? Yeah.
Not moving them to a new space, but they're moving distance, their variance from the latent variables that you generated, and you're plotting two latent variables essentially from two tables onto a space.
Yes.
So they're not moving the data point itself to a new space.
Yes.
Okay.
The new space is here.
Yeah. Okay.
When I rotate this, it's already putting them in a new space. Here, this is just to visualize what I mean by maximizing covariance. I'm just plotting them in a new graph when I put them together. Yeah.
I don't know if you do this after, but do you have like a tangible example of these variations?
Yes, I have examples of that. Which is coming. So I have cognition and the brain system that I showed you earlier with the non-centered PCA. Right. So this is just an example of the brain behavior correlations and how we could see that. Okay. Take a deep breath. We're going into math. So what I just showed you is how we visualize and how like what PCA and PLS means geometrically. And I hope that will give you a good idea of what we're doing with it. But to understand how we interpret it, how we do the analysis and the details of it, we cannot avoid equations. But I'm not going to show you too many equations. There's just one, but it wouldn't be very obvious. I'll try to make it small. So let's go back to the PCA. I'll go slower this time. So again, we have observations. Variables, just the original data set. And remember the linear combinations here. We got the first factor. Okay. And then we call these coefficients loadings. And just so that it will be easier for us to understand further, I want to clarify the terminology first. Here, I'm calling the 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 new scores for the observations factor scores. And the factor scores plus the loadings is what I'm defining as a component. Okay. Once I get the first component, what I do is I subtract my first component from the original data set. And then I repeat the procedure. I find the different set that captures the most variance in this residual data. And I got this my second one. And I repeat this until I have no information left in the data set. Make sense so far? So that means all the information captured by my original data are now in my factors. There's nothing left. And that's what PCA should do. It's just helping you to reduce the dimension of your data, but also give you a more concise way to understand your data. And they do it by computing this linear combination of your original variables because these variables might be describing very similar things. And I'm now just trying to put it into like orthogonal slices of the data. Okay, so you see this process of subtraction, and that's the process of deflating my matrix, reducing the dimensions. So that's also like this process is also why we ended up with orthogonal things. So I got my first component. One is subtracted. There's no information from component one exists at this point, right? So that means when I got my second component, it's not going to be correlated with component one at all. So what I'm showing you is that this process of subtraction is what ensures the components are orthogonal. And this is actually the process that you can do with like an iteration to estimate your PCA results. Okay, here comes the math. So I'm describing you the process, or it's more like a thought process when people first develop PCA. But later on, we found out that, oh, there's actually a very convenient way to get that in one single step, and that is the singular value decomposition. So instead of like iterating through all that process of subtraction and estimation, we ended up just doing this SVD. And it's a very nice way to do it because with SVD, it's usually a core function in all the programming language, and you will always get a unique answer from it. Whatever, if you put in the same data set, it will always give you the same output. So it's very reliable. So what SVD does is that equation, basically. And that's the only equation behind everything, PCA and PLS. And what it does is it's decomposing my original data matrix X into three different matrices. These three different matrices is capturing different part of my original data set. So because the singular value decomposition, we call this left singular vector because it's on the left side, and the right singular vector because it's on the other side. Nothing really meaningful in that. So the left singular vector and the right singular vectors are describing my rows and columns with my new components. So now I have my rows, original rows described by the components. I have my, this is transpose. So I have my original columns described by the components. So these two matrices are doing the rotation for you. So it's giving you the linear combination, and it's basically rotating the space. In the middle, we have what we call the singular value. And this is described, this is just capturing the variance of the space. So in general, what SVD does is I'm trying to show you to get to these components, how I'm rotating it and how I'm stretching it. So one thing about these factors is that each component of the singular vector only has a variance of 1. So it's only doing the rotation, it's not doing the stretching. All the variants are stored here in the singular values. So that's how it's giving you like a full decomposition of this. And this is also how we save some complex data sometimes, because if you have ever run PCA, you would know that sometimes you will only have, like, for example, 3 very important components, and the rest are like not important, doesn't explain much, it's more like a noise. And so sometimes people would remove those components and only keep the first few that are informative. And with this process, instead of storing this in a computer system, I would only spend like a smaller space if I break it down like this. Okay. So these are the singular values, and this is a diagonal matrix. So these are the zeros. Else. Okay. So this is a decomposition. I could also, from these matrices, build back what my data look like, one component at a time. So I can see, okay, if I'm only considering my first component, what my data would look like. And I do that for different components. And when I add them up, it will build back my original data. Yes.
Just curious, say if you do have like a lot of noise within your original matrix, could it be possible that you have like an infinitely large number of factors so that you cannot build things back?
No, that's a great question. So there is a limit of how many components you can have. The limit of your component will be the minimum value of your number of rows and your number of columns minus 1. That's what we call the rank of the matrix. And that means how many dimensions at the minimum that I know could have captured everything here.
Yeah, it's a degree of freedom.
Yeah, it's like the degree of freedom in a multivariate space. So because I'm already describing, for example, if I have 8 rows and 10 columns, I can describe this data set. I already know how to describe this 10 data set in a 10-dimensional space with the columns, or the 8-dimensional space with the rows, right? I already know that. But PCA potentially could like shrink that for you and identify what is how many like meaningful dimensions there are. But the maximum is either this 8 things. And when I have the -1 is because in PCA we usually subtract, like we usually standardize the variables. So once you have the mean, you lose 1 degree of freedom. So there is a limit of components you could get, and it's either I-1 or J-1, whichever is smaller. That makes sense? This is actually an important point that we might know later, because that means if I only have 3 people in my data set, I could only have 2 components next. Even if I have like 100 variables. Okay, so that's why increasing the number of participants will help us increase the power, is because we're going from a larger dimensional space down to a smaller ones. And it's the same for the variables. If I only collected 5, then the maximum number of components I could get from PCA is 4. Okay, makes sense so far? Okay. So remember the coefficients that I showed you earlier that we used to build the new factor scores? They're stored in this queue on the rows. Like if you rotate it, it will be on columns. And this is how we compute the factor scores that represent the observations. That equation is the equation for the linear combination. So I have my original data X and all the coefficients in Q. And that's how I got like the scores for the observations. Then to interpret a different way to interpret the component, aside from just looking at, what is like age or sex effect in that space, we could also look at the loadings, like what these factors are made up of. Right, and that's the coefficients we see, and we can look at them one component at a time to interpret these dimensions too. So that would answer Camille's question earlier, that's a different way of describing the components too, by looking at what variables contribute to this component. Because maybe not all the variables are informative and are important in building this component. So that's why we're going to the loadings. Yes.
It's the same as eigenvectors.
Loading is the same as eigenvector, yes. Factor scores. Do I want to add this? Okay. If this makes you more confused, then just ignore what I said, but if it's helpful, then I'm going to say it. So this is a linear combination, right? My factor scores. If you play around with that equation, you will see that it's also P times delta. So X times Q is P times delta. So factor scores is singular vector times the singular vector. So you rotate and then stretch, and that is your space. That is your scores. If that doesn't make sense to you or that makes you more confusing, just remember it's a linear combination, and that's good. That's all we need today. So that line is the SVD, and SVD has a constraint because when I'm decomposing things into these matrices, I could have like millions of answers, right? What makes this solution unique is this constraint that the components here, the vectors, the singular vectors here are orthonormal, which means the loadings of different components are not correlated, and they have a variance of 1. And this is ensuring that it's orthogonal and my solution is unique. And this orthogonality will propagate to the factor scores too. So if I correlate my factor scores, this will be my correlation matrix of my factor scores. So the variance are diagonal, and they all have 0 correlations to each other. Okay. So now we're extending that to PLS. It's very similar. So PLS, now we have 2 data sets. What PLS does is we first compute a cross product matrix. So you can think about it as a correlation matrix, but sometimes if we don't like standardize these scores, then it's just a multiplication between the two. But this is the matrix that tells you how these variables co-occur with each other. Right, so I basically have something like a correlation. And then let's put this into SVD, which we've already gone through. Right, but remember how SVD is describing the rows and the columns in the singular vectors? Now my rows are variables of my first set of first table, and my columns now becomes the variables of my second table. So everyone wants piece of fun. So we'll come back to that, but if we go back to the linear combination, remember the rotation from the two space? What it's doing is it's extracting the factor score respectively from the two tables by creating respective linear combinations from the two tables. And in PLS-C scenario, we often call these factor scores latent variables. And that's what you will hear. These are the new scores for the people that's describing the people. And they together should have maximum covariance. And then we subtract it from the two data sets to get the second set of the variables, and they'll have the second largest covariance compared to the first, and so on. This is just the math behind that two rotation. That makes sense? Any questions? Yes.
Do we ever try to see the covariance between like first factor of X and second factor of Y? We do things like that. Does that make sense?
Yes, but if you can tell, they will have a correlation of 0. Sometimes we do that, but not much. Like rarely did we do that. We usually look at them one component at a time. I do want to bring this to your attention, but I think this will come back next. Yes. Okay. So what this is doing is actually deflating this correlation matrix that we showed earlier that we put into the SVD. What is special about this is it will bring you a very special case of orthogonality. Remember in PCA, we have component 1 orthogonal to component 2 to component 3 and so on. In PLS, if you look at the singular values matrix, so this is if we correlate my latent variable X to my latent variable Y. And the rows are first and the columns are corresponding to the components. You'll see that these first two will have the maximum covariance, but that will be orthogonal to the second component of the other table. But it doesn't mean that it's going to be orthogonal to its own second.
So it's like the plane or we're showing that so much there.
It's like yeah, it's the plane. It's orthogonal in this space, but not in the individual table. So I have, for example, here I have 3 components, right? That I got from PLS from each table. They're not orthogonal to each other within the tables. They're orthogonal that this variable are orthogonal to all of are orthogonal to these other variables.
Yeah, I agree.
From a different table. That makes sense. Hassan, you look confused.
Trying to wrap my head around, so latent variable 1 from table 1 and latent variable 1 from table 2, they come together,
They have maximum covariance.
and these latent variable 1 and latent variable, both latent variable ones from each table, they represent the eigenvalues, correct? Like, it's not like the first, like, I'm kind of confused.
These are the eigen vector times the eigenvalues.
Okay,
No, these are not. These are the so the vector gives you the coefficients.
Right.
And then you need to build this back by multiplying them to the original data.
Okay. That was my question, because is latent variable one and latent variable one from both respective tables, they're not independent variables from like the original data set. They're like mathematically different things that came from this eigenvalues. And
Yes.
eigenvalues into factors.
They are computed separately.
Okay, so gosh, that's where I was looking for.
Okay. But I just wanted to mention the orthogonality because it's not very straightforward as in PCA. So this is where I'm showing how it's computing. So I have my loadings for X now in P and my loadings for Y in Q. And I take the first set of loadings, multiply by my original table to get my latent variable. And that's my x-axis here. And now I take the first component of my loadings y, multiply by my original variables from y table to get the linear combination that gives me the latent variable of y. And when I plot them together, I will see that space. And just a reminder, you should always see your people or your observations going on like this diagonal line, because that's what PLS is maximizing. If you're running PLS, that should be the pattern you see. If you see something that's very scattered, that might means that the association that's originally in your data set is just not so prominent. The effect size is not so big from the beginning. Okay, and then now we can also look at the loadings that contributes to this dimension from the respective table. So in PLS, the latent variables, like the new scores with the loadings together gives me a component, and then the component for my data X and my component for my data Y from the two tables together build a dimension. This is just how I want to synchronize the terminology here. So again, the orthogonality are ensured by the constraint in the PCA, and it propagates to how the latent variables are orthogonal to each other. Okay, if the orthogonality part is confusing to you, just forget about that. We usually wouldn't, that usually wouldn't bother us when we do the analysis. But now we're back to how we interpret the component in PLS. So remember how we interpret it in PCA, we look at the progression. We will do the same thing in PLS. So here I have the observation, right? I could also look at how the observations are distributed here on this dimension of PLS. So for example, if this is age, then I might have like younger versus old here that goes on this diagonal, and that would mean like this dimension of PLS is capturing the age effect. And then we can interpret remember how we build these factor scores. So again, the scores that we're plotting there is these ones. And that's what contribute to these factor scores. So I take a linear combination to build that, right? And so we can look at what contributes to it to interpret them. So for example, I have the orange team versus the red team, and that's capturing the association of these variables versus these variables. So you have people in this quadrant and this quadrant, right? And that's capturing the association that goes on the negative end of the two tables versus the association of variables. The association of variables that goes on the positive end of the variables. And then we can map them onto the groups too. So we will say these darker variables are more associated with group A. The lighter variables are associated with group B. I'll show you an example later, and then we can see if that interpretation makes sense. So latent variables are also under different names. So you might see people call them factor scores or sum scores. A lot of literature will call them like brain scores, behavior scores, social cognitive scores, whatever new scores, they'll just put the name in front of the scores to mean latent variables because they're new scores. And loadings in PLS literature, can you see from here? You guys see. So the loadings, sometimes people just refer them to singular vector or saliences. That's also specific to the PLS literature. Okay, so let's go back to the brain and I'll show you how we interpret that, the PLS results. So remember how I got the scores from my connectivity and want to relate it to the behaviors? Now we bring the PLS. So just a quick background on what my data is. I have a transdiagnostic data set. I measure social cognitive scores from autism and schizophrenia across 2 studies. So this is my sample size. And instead of resting state, we look at test connectivity. So the map that you see earlier is from a social processing test where participant will watch a video of someone describing an event. They need to rate how positive or negative their emotion is. And I take the functional connectivity from that task, decompose it to give me the map I showed earlier, and I want to see how that relates to my social cognitive performance. So if we go back to this map, another nice thing about this method is because it's similar to PCA, remember, we could build back the data set from each component. And that's very helpful when we're looking at functional connectivity because it will show me what pattern is captured by different components. So for example, here I have component 1 capturing the systems that are shown in that connectivity pattern and component 2 with that pattern. And it will represent the segregation on the different components, right? So we see component 1 is separating the visual systems from the language and auditory networks, which map onto the 2 blocks you see in the reconstructed pattern from a component 1. And the same thing for component 2 as well. So if like today, you can't really tell what your components are from just looking at the loadings or the scores or the demographics. Another way of doing it is to reconstruct your pattern and to see what pattern is actually captured by the components. And sometimes that will give you an idea of how to define this component. Okay. So I ended up with this map. And we define the first component as the perceptual axis because it's capturing the progression from the visual system to the language/auditory system. The second component is a little bit hard for us. So instead of like just looking at these canonical networks, we decided to group the brain regions according to a different set of networks. So we look at the 2 social processing networks. So here the mentalizing networks are the higher level social networks that is responsible for higher level social cognition, like theory of mind, trying to understand others' perspectives, versus the simulation networks that are usually responsible for lower level social cognition, like basic emotion recognition. And you can see that it's pretty well captured on the second dimension. So we define the second dimension as social axis that captures the segregation between the mentalizing and the simulation networks. So we got these scores from my non-centered PCA. The definitions of the component comes after. This is entirely post hoc, right? I did not put into the network information. I did not put the network information into my PCA at all. So I just map them onto the map and see what what makes the most sense when I'm describing the distribution in the space. So I put these two dimensions in my PLS and I want to correlate it. And so here I narrowed down to only include the brain regions that are in the social networks because I'm most interested in the social networks. I want to see how the social processing networks interact with each other in different groups and how that relates to their social cognitive performance. So I'm not looking at whole brain. And then I'm associated with the social cognitive measures here. This is what I got. So these are the loadings from this is what contributes. These are the social cognitive performance that contributes to my first dimension. So you can see that everything is going in the same direction, which means you will probably see this a lot if you run a PLS, like everything is going in the same direction on my first component, and that's because sometimes or most of the times your measures are capturing the same thing. For example, my measures are just capturing how people perform, how well people perform social cognitive performance, right? So this first dimension is basically capturing the severity of their yields. And it's related to this pattern that I'm showing in this Cafsata space. So we found that overall better social cognitive performance is related to increased network segregation. So they're moving away from each other along the perceptual axis, but more integration between the two social processing networks on the social axis. When I looked at the latent variables, I could see that I have healthy controls versus the two patient groups. But the patient groups are not significantly different from each other. And you can see this progression on the diagonal. That's the association that the PLS is capturing. What is interesting is that if I go back to my perceptual axis and actually color the brain regions according to the social networks instead, I would see this pattern. And if I did not do a dimension reduction, if I did not take a dimensional approach, I might say that I found increased social network segregation. But because it's on the perceptual axis, when it's moving like that, it looks like they're moving away from each other, but they're actually not, right? Because they're moving in parallel to each other. As opposed to on the social axis, they are actually moving towards each other. But this is the pattern we found in our previous univariate analysis. But what we see on the actual social axis is what will be hidden if we didn't use the multivariate approach. Okay. Any questions so far? No? Are we all good for just doing a PLS? No? So going back to the interpretation, so you see this is how I how I interpret this as the general performance is because I see this progression from the patient group to the healthy controls group. So from the negative side of the component to the positive side of the component was capturing the progression from patients to healthy controls. So now if I'm looking at the loadings from the negative side to the positive side, it's capturing the pattern of my patients, which is worse performance, compared to my healthy control, which is better performance. And that's why you see they're all going on the positive side. It just means that my control groups are performing better than my patient groups. And that's what I meant earlier when I'm showing, how we interpret PLS, that we're mapping the group segregation on the latent variables to the patterns in the loadings. Does that make sense? You know? Any questions so far? I'll give you some time to think about it. Let me know if you have any questions. I want to show this one. That's what I'm talking about. And this is the most important thing I wanted to get from PLS, is how we interpret the dimension. So the components, this dimension of PLS is capturing the association between two sets of variables. And it's basically these variables on the negative end versus these variables on the positive end. Sorry, negative end, positive end. And is associated with the segregation between the groups. Okay, we all good? Any questions? No? We're going to take a break here because I'm going to go into the real stats after this. We're going to go into bootstrap and permutation, and I hope you're not too tired. But let's take a quick bathroom break for maybe 5 minutes. What time is it? Oh, it's already 11:44. Okay. So let's come back around 11:50 and then we'll continue with the rest. Can you pause? Okay, I think we're back. So, any questions so far after the break? No? Okay. So now we're going to talk about inference analysis for PLS. So we see the results of PLS, but how do we know whether it's meaningful, reliable, or not? Like we talk about significance, we talk about effect size in univariate analysis. We want similar ideas for PLS. So is there anything in the data? First of all, are the components real? Usually with multivariate analysis, you'll have a scree plot like this that gives you how much variance or covariance for PLS, like each dimension is explaining. And from the scree, this is called a scree plot. From the scree, we will decide like how many components are really meaningful to be kept, right? And there are different ways of deciding it. There's like the Kaiser test, which is just comparing it to one, or you have like you could also just look at the elbow. So you look at when that linear trend change and you take what's like above the elbow. So in that case, I only have like one dimension. So there are different ways of doing it. I'm going to talk about how we tested today with permutations. So it's like a null hypothesis testing. It's called permutation test. And what you do is you resample without replacement. I'll go into the details of the process later. The other question we will have is when we look at the loadings, how do we know that they're important? So we will have a set of loadings. Yeah, we can show them with bars, but how do I know how big is big enough, right? How important it is that we can use it to interpret our components. So to do that, we look at how significantly they are different from zero, and that will tell us how reliable they are. And it's using bootstrap test, which is resampling with replacement, and that's the core difference between the two, which I'll mention later. And we have a new measure called bootstrap ratio that we use to indicate whether it's significant or not. But we also want to know how important the variable is because significant does not mean important, right? Significance doesn't mean you have a big effect size. We will also look at how important these, like how big the effect size is for each variable. We know how much it contributes to this dimension, and we compare it to the average contribution. Okay, so let's start with the components, the permutation test. So permutation test is basically it's a non-parametric test, which means it does not assume your data follows a distribution. And we have been doing, it's similar to like all the null hypothesis testing, like t-test, z-test. It's just that these tests have a distribution that you compare to. But in permutation, I'm building this distribution with my own data. I'm assuming my data is the best representative of the population. And then I'm building this null distribution from my data. So to permute the sample, you break the bonds in the data set. So for example, I have a set of faces. So these are my observations. These are my participants. And I have 3 variables that I collected from them. To do a permutation on this data set, I break the link between the people and the data. Okay. So here are all my participants. I have a hat to do my permutation. I put all of them in my head. I shake it. And then I resample it. So I first take one. Okay. So you can see that I'm resampling without putting them back into the hat. So I'm resampling without replacement. I'm basically just shuffling them. So changing the order of the faces. And with that, I'm breaking my relationship between the face and the variables. Then what we do next is we repeat this process multiple times, usually 1,000 times. And just remember that after we do that, when we're normalizing it, because if, for example, we're computing PLS, right? We're always normalizing the variables. When we're normalizing it, you need to use the original mean of the variables and the original standard deviation. And you will not just shuffle the image. The image is like one of the variables in this example. Usually we will also shuffle the by columns. So you break the links between all of them. And that means when you're looking at the association, because that's how you resample the data, there should be 0 association, right? Because you already like mixed the order. And that's how we built the null. So after we do that, we normalize them and then we compute the PLS and we create. So when we compute the PLS, we will get like 1 PLS result out of each iteration. And we ended up with 1,000 PLS results that we can build a distribution. Distribution of our singular values, distribution of our loadings. And then we compared how the observed value is compared to this distribution, which represent the null. So when we build a distribution, we're building this when the links are no longer there. So we're saying what the distribution will look like when the null is true. And then we compare our observed value to this null distribution to determine whether it's significant or not. Just like what we do with t-tests and z-tests and everything. So for example, I will have like 1,000 of them, and here I'm plotting the singular values. So the basically the level of association. So each value will be stacked here as like a pixel. And then when I draw it a second time, if I find the same thing, I'll put it here. And then together with 1,000 cases, I have like a histogram like this that represent my null distribution. And I'm comparing what I observed, so what I originally found compared to this null distribution. And then I can compute the p-value by looking at what is the probability of having a larger value than my observed value with respect to this null distribution. So what you do is you count the number of values larger than your observed values, divided by 1,000, which is the total values to build a distribution, and then I got my p-value. That's the idea of the p-value too when you do like all the univariate tests. Does that make sense so far? Is there any questions? No? Okay. So you could also look at it like dimension by dimension. So that's how we do the permutation test. What it will give us is, it will tell us how significant our dimensions are, whether it's explaining a significant amount of variance. Okay, so for the variables, we're using a different way to test it. We're looking at how reliable they are using bootstrap test. So bootstrap is slightly different from permutation, that we're not breaking. So again, we have the same data set, but we're not breaking the links anymore. Now the observation stays with the same set of values. And with that combination, we put them again into the hat. We get one, we put it back. Okay, so this is the first, and then we put it back. We draw it again. We got a second one. And we repeat that until we have a full new sample based on our data. So this whole process is assuming that our original data is our population. And we'll see, like, with different resampling process, how extreme could our data set become. And as you can see here, you can have repeated cases, right? But this is just showing you how extreme it can become so that we can build a confidence interval around our observed value to see how stable it is. Wait, so then does that make sense? The difference between permutation and bootstrap? Okay. So it's resample with replacement for a lot of times, usually 1,000. And after you do that, you will compute a PLS from each of the new sample. And again, you build a distribution, but now for the loadings. So that is showing us how varied could my loadings be if my data best represents the population. So from this distribution, we then get the mean, which should be really close to what we observed at the beginning. And then we get the standard deviation. And with that, we could compute this bootstrap ratio, which is an analogy to a t measure. So we have mean divided by standard deviation. Does anyone remember how you compute your t value? It's mean divided by standard deviation. So usually it's mean, if you're doing like a two sample t-test, is the mean of sample 1 minus the mean of sample 2 divided by standard deviation, or you have like a pooled standard deviation, right? If you have this, it's equal to the mean minus 0 divided by standard deviation. So I'm basically testing how different my mean is different from 0. Makes sense? So that's bootstrap ratio. You will see bootstrap ratio a lot in PLS literature. People will sometimes interpret that as effect sizes, which you should be really careful about because that's not what it is. It's not effect sizes. It's telling you how significant it is. Okay. So I have the t-statistics, but just like the normal t-statistics, well, I have the bootstrap ratio, but just like normal t-statistics, I need a threshold, right? I'm comparing to my z. And so usually in brain imaging, we only keep the t larger than 3 because usually we have a lot and then we need to do multiple, we need to correct for multiple comparison. But the normal one is 2. And why 2 is because basically this idea of z of t is the same as the idea of z. If you look at the equation of z, is pretty much the same. It's mean divided by standard deviation. And remember the criteria we use for z at 0.05, 1.96. Does that value sound familiar? and 1.96 is very close to 2, so we just round it up to 2. So in bootstrap ratio, we usually set the criteria of bootstrap ratio to 2. If it's larger than 2, it means that it's significantly different from 0. Okay. So very important thing, significant does not mean important. So it just tells you how different it is from 0. And when we do bootstrap, if you have a design in a group, for example, if you have patients and healthy controls, sometimes you want to keep the structure of your data. So let's say if you have half of it being patient and half of it being healthy controls, you might want to make sure that every time when I resample, I still have half of my resample data being patient and half of it being my controls. So you would want to resample within the groups instead of across the whole sample. So this is just something to think about when you're doing bootstrap. Okay. And because it doesn't mean important, so we need to look at effect size when we talk about the importance of a variable. And that's when we compute something called contribution in PLS. In PLS, contribution is the square loadings. So remember the coefficients? We squared it to quantify how much it contributes to the variance of the dimension. And the reason that we square it is because it's additive. And then we will compare this with the average contribution, and the average usually we compare it to 1 over the number of variables. So if I have 8 variables, my average will be 1 over 8. And that's because we assume that each variable contribute 1 unit of variance to the dimension. And so if they contribute more than that, then I would think that it's important enough. An important thing is that don't sum or average your loadings. If you want to add them up, for example, if you want to compute a mean across a set of loadings, make sure you square them before you add them or you compute the mean of them. And that is because, for example, in PCA, we have these loadings. And let's say for this one, this loadings that we're plotting here. So it's composed of my loadings on my first component and my loadings on my second component, right? And so A and B, these are my loadings for my first component, loading on my second component. And this is if I'm plotting my loadings in the same amount of space. The reason that why we square it is because of Pythagorean theorem. If we don't have that, if you just add A plus B, it's not going to give you C. It's not going to give you the overall variance. Make sense? So C squared is the variance, and you can break it down into how much of the variance is from component 1, A squared, how much of variance is from component 2, B squared. So remember to square it before you do anything. If you plot the contribution and bootstrap side by side, so here I have 2 sets of data. Contributions are here, bootstrap ratios are here. You can see that they have very similar patterns, right? So that means when they're important, most of the time they're also significant. But you do see some significant variables that did not contribute that much variance to the dimension at the same time. So what I'm showing you is that roughly they have similar patterns. They don't always equal each other. But the contributions ones are really showing you the effect size. And I think this is what you want to show in your results. For the significance, is just telling you how significant these bars are, how significantly different from 0 they are. Okay, so back to the example I showed earlier. Remember the bars that I'm showing you? I talked about them as loadings, right? But I lied to you a little bit, just in front of you. They're signed contributions. So I'm actually plotting contributions because it's giving me the effect size. And it's signed because they're square loading, so they're always going to be positive. So I need to add the signs to them. And I got the signs from my factor scores, from my original loadings. So I keep the pattern. But I'm plotting it to show the effect size. And usually we would add like asterisks when they have like bootstrap ratio larger than 2. Instead of just showing bootstrap ratios as a different bar plot because it's usually very confusing if I do it that way. So we just add asterisks to the bars. A different way of plotting is that, remember we talked about the threshold for a contribution is 1 over the number of variables. We can add that to the plot and find the one that contribute more than average to identify the more important ones versus the non-important ones. And to break it down for you, the arrows that I'm actually plotting here is also sign contributions. And it's contributions because I need to sum it up, because these arrows for each network are actually from the summation of the arrows of all the regions that belongs to that. And in order to compute the summation at the network level, I need to first square it. So I need to first get the contribution and then sum them up. Then I have the latent variables, right? And if I zoom in, this is where I'm showing another bootstrap results. These are group means, so the triangles in the middle. And then I use bootstrap to estimate how stable the means are. So you could draw like these bootstrap confidence intervals around the mean. If they overlap with each other, it means that they're not significantly different. If they are like, if they don't overlap, that means they're significantly different. Similarly, but I didn't show it here, what you could also plot like the arrow bars on your contributions by bootstrapping it too. So you could show like how stable the loadings are as well. There are also other ways of examining the reliability, for example, the k-fold cross-validation or the split half. And nowadays, if you're running PLS, there is a very high chance that the reviewers will ask for this. Okay, any questions about that last part? I'll bring this up. Okay. Any questions here? No? All good? Okay. So finally, just the last bit. There are different flavors of PLS, and you might see this in a lot of imaging analysis. So here, you can think about the phases as brain imaging, the brain images. I'm just using face to represent it. That's easier to see. So all the imaging data goes into one single table. The other table could change. Sometimes people would put contrast in it so that when you do PLS, you're finding dimensions of contrasts. You could also have like group coding in a different table. So you're doing what's called a mean standard test PLS because it was first used on test data. And then you can look at specific activation that's related to different groups. There's also seed PLS in imaging, where so imagine this brain kind of based. You pick a seed and you put that into the other table, and then you do a PLS, so you're associating these two seed with the rest of the image for your brain. And then you can look at the dimensions that's capturing the connectivity to the seeds. Okay, so this is the last part. Things to know and think about. So first of all, there's a problem with the permutation test. So the test that I just showed you, there is an issue with that that's worth keeping in mind is that remember when we do permutation, we resample and then we do PLS. But remember how we get the components? We get component one, we subtract, then we get component two. That means my component two depend on my component one. My component three depend on my component two and one. And when I resample, that dependency will come into play because my original sample is different. And they will have different component one, so their component two are entirely different. I don't think you can compare across them. So there are actually ways to, like, there are different ways to solve this issue, but for now, I think most of the time we just ignore it, like we don't go beyond second. And it's kind of okay because when you ignore that issue, it's just going to underestimate your effect. So you're not going to end up with a false positive. It's just that you might have a false negative, which if we're being more conservative, it's okay. But there are different ways of doing it, and that is like dissertation for someone. So I wouldn't go into that. One thing that we've tried in our lab is to do the permutation, get component one, and then subtract the component one, and then do the permutation again. So we treat each dimension as component one to run through the permutation. The second thing, and I think this might be related to your data, is that PLS is immune to multicollinearity. So it's okay if your data are related to each other. PLS wouldn't break. It would help you capture it. But if you have too many things that are multicollinear, it will definitely be driving your dimension. So if you put like 10 redundant information plus one something new, then it's unfair to ask PLS to give you something that's not driving by those 10, right? So just remember that the more the more variables that's capturing the same thing, the more likely you're going to see the pattern because that will be dominating your actual pattern. The other thing is preprocessing. And by preprocessing, I mean how you normalize the data before you put it into PLS. So that goes back to Hassan, your question earlier. And that is because in PLS, we're decomposing, remember this matrix? In SVD, this is the correlation matrix. It's the correlation when you standardize your variables of the tables. Right, and then when you just standardize them, multiply them, you get correlation, you get Pearson's correlation. This is, I think by default now for most of the PLS function, but you might want to do something differently. So it will depend on what your data is. So first, the preprocessing includes two steps, centering, so removing the mean, and normalizing, which is removing the unit of the variance. And that's what, like, the basic of Pearson's correlation. There are also different ways of normalizing. So you can normalize to standard deviation equals 1, or sum of squares equals 1. I usually go with sum of squares equals 1, so that each contributes 1 variance, or not if the units are the same. So you're subtracting the mean, and that, like with that step, you're saying, okay, I'm putting everyone onto the same level as the mean, and I'm looking at the pattern with respect to the mean. But you only do this when mean is what you want to compare everyone's data against. If you have something that's meaningful, if you have a meaningful criteria, then maybe that's the thing that you want to subtract from. Earlier I was talking to Hassan about connectivity, right? If I have connectivity data in my PLS, I probably don't want to subtract my means because in connectivity data, 0 is meaningful. The positive and the negative signs are meaningful. They mean something real and in my functional connectivity. If I subtract the mean, that means I'm going to like adjust these values a little bit, and my negative connectivity might become slightly positive, or my positive connectivity might become negative. And that's not what I want, because that would imply entirely different things in my actual data set. So in connectivity, I never center them. Normalizing is when I remove the units, I remove the variance of the data. And you only do that if your variables are on different units. So I also don't do that when I deal with functional connectivity, because they're all Pearson's correlations. They're on the same scale. But these are the things that you might want to think about when you do PLS, even when it's just behavior. So, for example, if all of your all of your cognitive measures in one table are on the same scale, then maybe you don't want to standardize it. If they have a meaningful criteria, then maybe you don't want to use the mean. So I would suggest you think about that for both of your data before you run any PLS. What PLS cannot fix. So it's amazing. I love it, but it doesn't solve all the problems. It doesn't solve it when you overfit it. If you don't have enough observations, you just don't have enough power. And PLS is not going to solve it for you. That's the same as the sample size. If you have messy data, PLS is going to tell you how messy it is. It's going to extract a dimension that describes your messy data. That might not be meaningful at all. So the quality of your data is still important. It's not something that could be resolved by any multivariate approach. Garbage in, garbage out, right? Also, PLS detects linear effects, just like PCA. So if you're looking for nonlinear effects, then you might need to think about something else or some other extension of PLS. Finally, if you don't understand your data and you just put it into PLS, the scary thing is it's going to give you an answer, even if you don't know even if you don't know what you're doing, right? So, but if you don't understand your data, PLS cannot help you with that. So make sure to understand what you're analyzing first before you run any statistical analysis. This is actually not just PCA or PLS, right? Okay, so that's everything I have today. Sorry, it's a little bit long and dense, but if you have any questions, please feel free to let me know. And there are tutorials online. I've shared on Discord, the channel group, an example code that goes through a quick example of PLS and how to plot the results. So just let me know if you have any questions. If you're doing PLS with MATLAB or Python, there are packages, and I think the most popular ones nowadays is the one that's created by Macintosh groups from Baycrest, and that takes care of brain imaging analysis, like PLS brain imaging analysis. One thing to be careful about is that by default, they have different ways of pre-processing your data, like centering and scaling your data. And it's not flexible in these packages. So you might want to read through the manuals and look at their pre-processing options, pick the ones that best fit your analysis. And that's everything I have. Thank you. Is there any questions? If you get nothing or are worn out towards the end, it's okay. The only thing that I want you to get is the first 30 minutes of animation. That's the most important thing, is to understand the abstract idea of PCA, PLS, and this dimensional approach. The details, you could always go back to it later. Any questions? No? I think we're good. Okay. So thanks everyone, and we can grab lunch.